Good morning, everyone. Today I'm going to we're gonna fill in some notes that are at the end of our chemistry packet. So what I'm going to do is I'm going to be going through this chemistry review guide. So it's a little bit longer, but we're going to go through all these notes, and then at the very end, I do have an assignment for us, which would be the test that we would have taken for the unit. I'm going to be grading it a little bit differently because of, the way we're learning. There's a lot, there were some lab activities that we were unable to do. So I'm going to keep that stuff in mind. I'm going to be grading this with some leniency and so forth. But you will have this test that you will complete. Now, obviously, you're not going to have the test in front of you. You're not going to have a physical copy, and I don't expect everyone to have a printer and whatnot. But you can view the multiple choice questions on Google Classroom, which is where I'm going to post it, and then on a separate sheet of paper or in a Google Doc, you can just put your answers on a single sheet of paper, just a list of multiple choice, kind of like an answer key, and then the short response, because most of the short responses are just a few words or fill in the blank or something like that, maybe a sentence or two. So it can all be done on a single sheet of paper. That way you can take a picture and submit it through Google Classroom that way for me. All right. But before you jump into that assignment, I think it's going to be very beneficial to have the review right in front of you. So I'm going to just be going through the review sheet through this. If you're very, very comfortable with the unit and kind of the material we've been going through, you probably could jump right to the test assignment. All right, but let's jump right into it. So the first thing in the unit we discussed were the difference between chemical and physical changes. And the biggest difference for chemical and physical changes was whether or not could you go back to the original state. And if you could go backwards, that's a good indication that it's physical. If it is a permanent change, it is likely a chemical one. There's also other indications that chemical changes are occurring. Usually a color change, an odor coming off, fire being created and stuff like that. So road flare burning. A road flare burning is going to be a good indication that that is a chemical change. Crushing a sugar cube. Now you're probably not going to get that sugar back into a cube form, but it's still just sugar. Its chemical composition is exactly the same. Crushing things is a physical change. Boiling water. Boiling water is sometimes a tricky one. A lot of people put chemical because there is heat involved, but it is a phase change. And because it's a phase change, just water going to water vapor, boiling water is actually a physical change. A piece of metal rusting. Well, once something rusts, you can't go backwards with the rust. You can scrub the rust off and stuff, but rust is just going to be a chemical change. Ripping a piece of paper. Ripping a piece of paper is going to be a physical change. Baking soda from vinegar. So if anyone has ever mixed baking soda and vinegar, you'll just get a small chemical reaction. You'll see a little kind of smoke come off. You'll see it bubble quite a bit. So that's going to be a chemical change. Sodium reacting with water. I think this is a video that I did show right before we kind of left in March. But sodium reacting with water, and we're not talking about sodium like salt. We're talking the metal sodium. It's highly explosive. So that's chemical. And sugar dissolving in water. The act of dissolving is not a chemical change. You can go backwards. You can let that water evaporate, and you'll be left with the sugar behind. So dissolving is a physical change. All right, the phases of matter. So these are the solid, liquids, and gases, and based on the forms down here, which one is which? Well, when it's in a nice, clear shape, those molecules are all clumped together, definite shape, definite volume. It's a solid. Then when everything kind of just takes form to the shape and kind of goes towards the bottom, still close together, these molecules, but this is a liquid. And then when the molecules are scattered throughout the container, that is going to be a gas. We're going to fill in the phase changes below here, and 4 of them you should be familiar with already, I believe. There are 2 new ones that we did discuss, which were deposition and sublimation. We'll get to those in just a bit. Let's go through the easy ones first. A solid to a liquid. And most of these you can think of, water, ice, and water vapor. Solid to liquid, ice to water, that is melting. Then a liquid to a solid, so liquid water forming into ice is freezing. Then a solid to a gas. So if you jump directly from a solid to a gas, this was the dry ice example. That is what we called sublimation. And then the other way around, if you were to go to a gas directly to a solid, this would be called deposition. And the last 2, liquid to a gas, so water going to water vapor, is evaporation. And the very last one, when a gas turns into a liquid, this is condensation. So those are your 6 major phase changes right there. All right, so that's our first page. Let's flip over. Now we're going to do an example of each of them, and I probably said a lot of them already. For each of the following examples, state which phase change is occurring. So ice turning into water, that's a solid to a liquid. So a solid to a liquid is melting. Carbon dioxide coming off dry ice. So remember, dry ice is just frozen or solid carbon dioxide. It's not actual water ice. So this is a good example of sublimation. Water sticking to the side of a glass on a hot day, that is condensation. Hail forming in the clouds. So hail is that goes directly from water vapor to a solid ice. So this would be deposition. Liquid water turning into ice, that's freezing. And boiling water to create steam is evaporation. All right, the next section. The diagram below shows gas particles at room temperature. And this is use the diagram below to answer each of the following questions. Which diagram would occur if the gas particles were heated up? There's one that's not very good, which is choice 1. Choice 1 is pretty bad because now it looks like these molecules are bonded together. And when they bond together, that means a chemical reaction is occurring. So it is unlikely going to be number 1. We're kind of just looking at what's going to happen. They're going to move faster and they're going to spread out. Number 2, it looks like they form some kind of solid or liquid. But choice 3 actually looks the best because choice 4 is exactly the same. The only thing I don't like about choice 3, even though it's the answer, it looks like there are less molecules. There's not going to be less molecules. They're just going to be further apart. They are going to spread out and they're going to move faster. So it would be fair to add some lines to represent that these molecules are moving faster. But there wouldn't be less of them, but they're trying to represent that they're going to be more spread out, which is true. Because when you heat it up, they will move faster and they will spread out further. So which diagram, if the gas particles were heated up, I would say diagram number 3. Which diagram would occur if heat was removed from the same until it freezes? So that would be going to a solid. So that gets rid of, let me get rid of these X's. That definitely gets rid of choice 4 and 3 because those are still in the gas form. I would say choice 2 because everything's at the bottom. They're bonded together. You can see the kind of like these little lines in between them, meaning they're bonded together. So that one would be choice 2. Describe how temperature affects the speed of the molecules. So the relationship is going to be as temperature increases, the molecules move faster. And they spread out too. But That's the major relationship that we're looking for. As temperature increases, the molecules move faster. Let's flip over. We'll do solubility, which solubility is the rate at which certain substances will dissolve at. So we have this chart right here. It's just asking us which substance has 60 grams dissolved at 13 degrees. So let's look at our chart. We have temperature as the x-axis here. We have grams of solute that will dissolve in 100 grams of water, meaning how much of a material will dissolve. Because remember, you can't take, sugar, keep adding it to water and expect all the sugar to dissolve if you just keep dumping sugar in there. There's going to be a threshold at which you will not be able to get a certain amount of sugar to dissolve. If you just do a little bit, you'll get it all to dissolve. But if you just keep on adding, there's going to be a certain point where it doesn't dissolve, which is actually going to be one of our experiments we would have done. And you can actually get a lot of sugar and not a lot of water. It's kind of cool. It's quite amazing how much sugar you can get dissolved in water, especially when you heat it up. But that's kind of what this diagram is representing. But it says which substance has 60 grams dissolve at 13 degrees. So I want to go right to 13 degrees, which I would say is right about here. It's definitely closer to the 10 than the 20, because halfway would be 15. So I think that's fair. If we go up, we hit lithium hydroxide first, but if I go across, that looks like it's over 10, so it's 11. So I'm going to say no to that. Keep going up. When do I hit 60? And I think I clearly hit 60 right here. So what line is that? That's potassium bromide. All right, next question, which is which substance has 40 grams dissolve at 25 degrees? So here's 25 degrees. And then when do we hit 40? Let's see. I hit this one. That's not quite 40. I'm going to go up more. Yeah, that's definitely 40. Ammonium chloride. Which substance has its solubility least affected by temperature? So this one you actually have to make an observation on the lines. And which line is if you think about the math, which one has the least slope? And I would say the one that has the least slope is lithium hydroxide. Look how much more it can dissolve from a 100-degree swing. Not that much more. It is an increase, but not much. That line is almost flat, where all the other ones are pretty steady and going up. So the one that is least affected, I would say, is lithium hydroxide. All right, let's move down to the bottom one. It says identify two variables that affect the rate at which sugar will dissolve in the water. We definitely talked more than just two things, but first and foremost, heat. The hotter the temperature, the more likely it is going to dissolve faster. Another thing you can do, especially based on the diagram, you have sugar cubes and crushed sugar. And which one would dissolve faster? Well, definitely the crushed sugar. Whoops. Another thing that you could do to increase the rate is you could stir it. You could stir the water to speed it up. Which is why when most people put sugar in tea or coffee, they'll often take something to stir it up because it would dissolve faster. Which diagram, first, second, or third, would the water dissolve the fastest in? So it's going to dissolve fastest, with crushed sugar and in hot. So I'm saying diagram number 2 is the best candidate for this sugar to dissolve the quickest. So second diagram. Let's flip over. Periodic table. Which letter would you place the following element in, which is SN, which is actually tin? So remember how the periodic table is numbered. The atomic number right here that I've circled is the best way to place it correctly in our periodic table. So if you look at our periodic table, here's 51. So 50 has to be right to the left of it. 50 has to be right here. So if you look right above it, it goes to 33. So it's not numbered from top to bottom. It's numbered from left to right. Because this would actually be element 31. And then we could go down here. This would be 84, this would be 83, and this would be 82. So the one that would be numbered 50 is B. So in which letter would you place the following element? B. Explain how you knew to place it. The periodic table is ordered by atomic number. Remember what that atomic number means. That's how many protons are in the nucleus of its atom. So you literally, as you go from left to right in the periodic table, you're adding a proton into the nucleus of the atom, as well as an electron. Electrons are a little bit trickier because electrons are free to move from one source to another. But for the most part, the amount of protons and electrons in an atom are going to be the same. Name all the elements that react in a similar way to chlorine. So those are all going to be the ones that are in the same group or family. So all of these, this is why this group right here, this is where chlorine is, and fluorine, and bromine, iodine, and astatine. They're in the same group and family, which is called the halogens. They all react in a similar way. So if they're all in the same column, and this is why certain elements appear on top, and this is why the periodic table has this kind of funky shape to it, it's because we want to group the elements that react in a similar way. That's why the video I showed you with sodium reacting with water, it was also had potassium. They were all in the same group. Those were the alkali metals. So name all the elements that react in a similar way. We're going to name all the elements that are remaining in that group, which would be fluorine, bromine, iodine, and astatine. All right. Use the following chart to fill in the number of protons, neutrons, and electrons of each element. So all these specific 4 elements can be found in this section of the periodic table right here. And this is actually what we did last video, so just over a week ago now. You just look at the atomic mass and the atomic number. So for oxygen, because oxygen is, so I'm looking at the 2 numbers here. It's 8, so that means 8 protons, 8 electrons. 8 protons, 8 electrons. And then for neutrons, you're going to want to subtract the atomic mass. You want to round it. This one is 16.0. Round it to the nearest whole number, which it's already rounded. Subtract the amount of protons, and that's how many neutrons you're going to have. So for carbon, here's carbon. It's got an atomic mass of 12. And it's got an atomic number of 6. So 12 minus 6 is also 6. Iodine. So here's iodine, which is element 53. So we have 53 and 53 here. Those are always going to be the same. Its atomic mass is 126.9. So I'm going to call that 127. And then we're going to subtract 53 from it. So I'm just going to do that subtraction really quick. We get 74. And then the very last one, krypton, which is element 36. So 36 here, 36 here. Its atomic mass is 83.8. So I'm going to round it up to 84 because that's the correct rounded value. And we're going to subtract 36. So this becomes 48. And that is my chart, which is exactly what I had to do on the other assignment. You actually had more columns you needed to fill out. This one just has you do protons, neutrons, and electrons. Let's flip over. Which substance in the chart are considered elements. So elements are, if you can find it on the periodic table directly, it is an element. If it has more than one capital letter, like this one, that's going to make it a compound. So that one's a compound. So which ones are elements? So oxygen, for sure. And then HCl, nope, too many capital letters. CO2, you're not going to find that on the periodic table. Water, not an element. Helium is. Helium is element number 2. So definitely those. In the chemical formula carbonic acid, H2CO3, how many atoms make up a single molecule? So you got to look at each of the letters that we have with their little subscript numbers that they have. So this says, this is one molecule, by the way. The whole thing is one molecule. But each of the capital letters represent different atoms. But the 2 in front of the H says it's 2 hydrogen. There's no number in front of the capital letter C for carbon. So if there's no number there, we assume it's 1, just like you would in math class. So that means there's 1 carbon atom. And then there are 3 oxygen atoms. So how many different atoms make up this one molecule? Well, it's 2 plus 1 plus 3. It would be 6 atoms make up a single carbonic acid molecule. And I think we've talked about carbonic acid in the past. Carbonic acid is actually CO2 dissolved in water. All right, tell if the diagram is an element, compound, and if it's a pure substance and or mixture. So we can only use the certain colors here, and there's obviously only 2 colors, black and white. But if they are single colors, there's nothing bonded, meaning they're not next to each other, that's going to make it an element. And if it's just the same thing throughout, that's going to make it a pure substance. So now we look here. Now they're bonded together, and there's multiple colors bonded together. So that's going to make it a compound. But is it a pure substance or mixture? Well, it's going to be still a pure substance, because look at the molecule. There's 6 of them. It's 6 of the same molecule. So it's still a pure substance. Then we get to this one. Well, we have this single color, but then you have these colors. You have black ones by themselves, but then you have 2 white ones bonded together. So that's going to make them, because it's the same color bonded together, we're going to call them elements. Usually we call them diatomic elements. Kind of like oxygen is one of these. Every time you breathe in oxygen molecules, you're getting 2 oxygen because it's O2. So these are 2 elements. But if there's 2 literally mixed together, well, it's no longer a pure substance. This is what we'd call a mixture. And then the last one to the right, well, you have 2 different colors bonded together, so you have these 2 shapes. Definitely, you have 2 compounds. And if you have 2 compounds mixed together, that's going to make it a mixture. Which I know is something we've practiced in the past, but I know it's been a long time since then. This question might be a little challenging because we never actually got to do this. This is something we actually, I would have showed you, we would have experienced it, we would have done an activity with this, but I'm just going to explain how we would do it. So it says a student is given iron filings, sand, and salt, and she places all 3 substances into water and are mixed up. So you mix up it's 4 things: iron, sand, salt, mixed with water. And then we're going to describe a proper sequence that would separate the iron, sand, and salt. So there's a few things here. When you mix all this in water, first thing's going to happen is the salt is going to dissolve. And because it dissolves, that indicates to me that water and salt should be the last thing that I try to separate. So how do I get the sand and iron out of our salt water? Well, we'd use a filter. So you'd filter out the iron, sand from the salt water. So now you have two different things. You have iron and sand after you filtered it out. And then you have, on the other side of it, you're going to have salt water. Well, so now we got to separate these. How do you separate iron from sand? Well, you could use some tweezers. That's going to take you many, many hours. The easiest thing to do is use a magnet. If you use a magnet, because iron is magnetic, to separate the iron and sand. And this is something, again, like I said, we would have done in class, and it's really cool how quickly a very strong magnet can pull all the iron out of sand. And it, you can do it in just about 5 seconds, maybe less. It's pretty cool to do. And then the very last one, well, how do you separate the salt from the water? Because the salt has dissolved, what you're going to need to do is boil the water. Because when you boil the water, all that water is going to evaporate into water vapor. You could collect the water vapor if you wanted. But salt doesn't boil, at least not at the same temperature that water does. So that's how you would separate the salt and water. Boil the water to separate the water and salt. And once you've done those three things, you'll have all four things completely separated from each other. And that's the end of the review packet. So remember, just to end this video off, I'm going to be posting this test on Google Classroom. So it's very important that you get it done. I'll give you guys about a week to complete it. If you were in class, I think it would only take you about 30 minutes. So if you spend, a few minutes a day working on it, you'll definitely have enough time to complete it. As always, if you run into any questions on the assignment, please email me, throw the questions in Google Classroom, whatever you want. I will help you through these. It's more important to me that you understand the content of the questions. I'm less concerned about you, trying to get the right answer and stuff like that. Feel free to use your notes though, and other online resources or anything like that. But good luck, and let me know if you need any help.